The first 3 weeks of the eruption here in Hawaii, crazy things would happen in the middle of the night. A new fissure would open up and it would threaten a new neighborhood. Thousands of people are evacuated from their homes. I started the Hawaii Tracker Facebook group to help people understand what's going on and get their questions answered.
Hey, how's it going? We're live. This is Fissure 20.
We had hundreds of people all throughout the neighborhoods sending in videos, articles, and images. We spent a lot of time making sure the accurate information gets out.
This is live. There's still lava moving.
They weren't just sharing a story, they were helping their neighbor. If a family was being evacuated, my group would just jump in and help out. So it was huge. They were watching out for each other.
Hello everybody, thank you for coming. Thank you for the support from everybody.
As we go through this, we're growing closer together as a community. When tragedies like this strike, you really realize how much you need each other.
Aloha everybody, I am geologist Philip Ong. I'm here with Mr. Dane DuPont, Hawaii Tracker, hawaiitracker.com, bringing you guys another Kīlauea and eruption update, and today also some Maunaloa update as well. So we are going to be taking questions, several points throughout the show. They're going to be collecting the questions and passing them on, manning our chats, and checking in our streams and letting us know if there's anything we need to be aware of. So mahalo Dane. And I will start the narration today with this view here. This is a video put out by the USGS Hawaiian Volcano Observatory, which is the basis for much of our information here. And this is a thermal video they put out viewing the west vent from the south. So this is the west vent over here, this west area. Well, that's going to give me text. That's not what I'm looking for. Technical difficulties here, but what you guys are seeing is the dark spot at the top is the west vent with the two glowing holes at the top, and then the double stream at the bottom. That's the brighter orange and red spots. Let's see if I can get my brush right over here. Okay, here we go. So up here, this is the west vent, right up there, and there's these two hot holes at the top. And are glowing, and it looks like there's been some lava spatter that's been flowing down the sides over here and here. So I'll play this. This is actually a fairly short time lapse. I want to say the whole thing runs 25 seconds or so, and it covers about maybe about a two and a half minute period of time. So it's not a whole lot of time. It's so actually when I play it now, it doesn't appear to move very fast. You see some of the gas venting up here, but not so much, very slow movement of a double vent coming out here. But it is moving. It's moving very slowly, but it gives you a better idea of in real time what it might be like. This is still sped up 5 times. So 5 times slower than what you're seeing here is how it would look in real time. And of course, we wouldn't be looking through the thermal. So instead of be seeing that thin silvery skin, that's the surface that forms in lava flow. So let me put that one back and play it one more time here. And this was taken March 15th, within the last week here. So rhythmic gas puffing is described for these areas up here. Otherwise, you can kind of see that our love island here, that area, has become attached to the perched rim of the lava lake. And the general pattern is that the lava lake is still shrinking. The double west vent entry is continuing. The depth has been unchanged in the last few days. It's still at 222 meters, 728 feet. The pressure cycles are still ongoing. Deflation, inflation just completed, the newest one. And our gas output's trending downwards, right, with our most recent SO2 measurements, down to 700, 650 tons per day. So we'll cover that in more detail here, but that's the main gist of it. Not a huge amount of change at the summit of Kīlauea as everything is happening in slow motion. I'm going to zoom in here, and it's the last 24-hour time-lapse from the USGS-HVO. You can see a very similar sequence now, except not in the thermal view, but glowing at night, and then silvery crest in the daytime with these harder blocks of floating rock, these smaller islands. And here we have the remains of the larger island that's now frozen in with this crest that's formed in the south part and in a north part of the lava lake. If I pan over here, you guys can see that a little bit better. Here's our island. It's now locked in place, and you'll see that it actually has been rising continuously this entire time, even though it's in slow motion. It's hard to see. But what's different is that this whole northern part is all frozen in now. The eastern part's been frozen in for a while. That was the first one. And it's wrapped its way around, closing off that crescent shape into this oval shape that we have over here now. So that's ongoing, still happening in slow motion. It's pulling back a little bit more. Here is a time-lapse released by the USGS of the entire sequence starting December 28th, about a week after the start of the eruption. So this is only a couple days after the west vent reactivates and takes over from the north vent. And so it's looped 6 times here. You can see that island is right here in bottom center. You can see it's rising. It does a spin and a rise. It's also interesting to look at the west vent over here and how quickly it gets drowned. Very quickly at first, and less quickly since then, as eruption rate has slowed and it's come up into that upwards flared crater. So let me put that one back one more time for you guys. You guys can see that rising island, and maybe what I should do is zoom in a little more here so you guys can see that west vent area too. I better put it back. Here, let's show you guys this west vent a little more in here. Oh, there you go, that's a little better. All right, so fantastic to see that sequence released by Matt Patrick, the USGS. And so more recently, this is just the last week, I put this together just so you guys can kind of see, this is just day and night now. So I'll play it here, and you can see no major changes. It's basically circulating in that bean shape the entire time. And there is that small pulse that happened earlier in the week, right over here, that ended up being a short burst that added a third entry temporarily, and then it basically stopped. It was an overflow of that crusted over tube system. So the double entry continues, and that's basically what's been a stable part of the lava entry here. So moving on, here are some of the photographs released. This is March 17th. St. Patrick's Day, and there is our rainbow leading into our pod of gold bearing, even in trace amounts lava. That's the...
Feels like I was lied to about what's at the end of the rainbow. That's how it ends.
Just a little bit harder to extract it. Yeah. Yeah. Yeah, I never said it was going to be easy, right? So there it is. There's the end of the rainbow. March 17th, and photo by Jay Chang. And let's move on to the next photograph here. And that one, March 18th by Kaylin, and it's pointing out here is that at the base of, let me move through here to the more high resolution version. You can see that at the base of the west vent here, there is now this pile of rubble, kind of a talus or a debris, like this whole side of the cone fell off and it crumbled in and made this giant pile, which is exactly what happened there. Let me pan it up a little bit. You can see this little gap right here, and you can see looks like there's some fresh lava that was this might have been a place where the lava might have been overflowing at some point in time. But this little bit notch right in here is evident, and definitely the back side is a lot higher than the front side, and you kind of see a broken off edge right here with a big gas bubble trapped on the inside, right? So you can see how frothy this can be. Let me zoom in even more for you guys to, well, that might be too much. Too much. Come back. All right. There are limits to how far you can zoom in with each tool, so I'm trying to get the max out of my system here. All right, so there, maybe that's the best I can do. You can kind of see that dark spot right in here is the center, a big gas bubble, and this big lava chunk lobe that globbed over it and trapped it in there. And that's the kind of feature that makes these spatter cones, that makes that north event raft, that makes that big island raft. And possibly some of these other smaller rafts that are floating in the lava lake, and that's why they're so light. You have enough of these things, even if it's smaller ones, then that makes the density a lot lower. All right, so yeah, fantastic documentation there of that rubble collapse, and we will look a little more closely. We'll zoom into the entry area over here on the right, and here is that view. Once again, March 18th by Kaylin, 7:15 a.m. So 2 lava inlets still supply lava into the lake, and this is actually a great resolution, so we can actually zoom way in and show you guys that exit point right there. And once again, it's really hard to get the scale of these things, right? If I pan over here to the left, maybe I should zoom out first. These benches on the side were something we were estimating before was on a range of 6 feet or 8 feet or 3 feet or somewhere in a range of a few feet, less than 10 feet, right? So that's, you know, if you were sitting down, maybe that would be the bench you would sit on, would be something that size. We want this all cool and the trail is established to get down there and all that, right? As if. In any case, it gives you some idea of scale. So the size of these channels is something along the size of a bus, right? Each one of these is more or less the size of a bus. You can kind of see there's at least on the surface, and possibly there's a split in the flow. The flow might be diverging a little bit. You know, there's 2 sides of that crescent, and the north side maybe is being fed by this side now, and the south side by this one. Perhaps. It's interesting to see how they actually diverge. And it's been steady, and essentially it's merged. But interesting to see how it's actually changing its shape there. So you can really see, now I zoom in, how quickly that silvery crust forms. Right here is where the lava is coming out, and only a few seconds later, at those slower rates that we're seeing now, time lapse really sped up in the thermal, right? It's forming that crust right away. So all this stuff is still liquid with this crust on top, but it's still moving, and that's the kind of action that we're seeing. The movement through, and then the foundering, the overturning of the crust as a heavier crust, and then sink in and be replaced by fresher lava. Right, and that's something we haven't seen documented in a little while, but the reports all keep mentioning it. That's still happening. Okay, so looking at the thermal imagery once again now, this is a regular f1 camera that's looking from the south. So our earlier view we opened. Our update today was looking from the opposite point of view. So now we're looking down at the west vent. Those 2 glowing holes are down here. And the double entry is here and here, putting lava to the north and to the south. And you really can see quite well how closed in it is here. And our most our most recent transient feature was this north bay up here, as I've been calling it. It's now receded all the way down. Only one little flow. Even this has stopped turning over with that foundering crystal overturning process. So it's really withdrawn quite a bit. We're still seeing all these islands, numerous ones, floating above the lava lake surface. And we are still having a lot of deflation and inflation events back to back, so that could be contributing to this as well. Right, we do see here there is this protrusion that's the attached quote unquote love island that one was featured on Valentine's Day as having a heart-shaped feature like that. It's become attached, and you can kind of see this. There's almost a line of these other ones here. Like maybe there's something shallower that the roots of these things are becoming attached to the sides as well. And so you might imagine that if this thing does close off any further, a likely place would be somewhere in this direction like that. And these are the kind of minute changes we're looking for, and we'll just wait and see what happens here. But interesting to see that these ones don't, maybe this one is still moving a little bit. And if that's the case, it makes it less likely that maybe just circulates through and pushes it out and around, and it doesn't actually close off. So interesting to see how that evolves. At the vent itself, not a whole lot of change here recently. The other flow was right over here. It's all cool over there now. It's just the two glowing pukas, the holes here of the west vent. All right, so one last thermal time lapse here. This is also covering the last week. So you'll see the burst here of that lava flow as it comes out, and then it dies off here at the end. There it goes. And otherwise, not a whole lot of change. If I play it again, we can watch the changes in the North Bay over here as it recedes a little more. So let me do that. And you can see here, at the beginning of the sequence last week, we still had lava coming up into these upper reaches, shallower part of the lava beach, so to speak, right? And since then it's receded more down in this direction. So slow motion changes going on still. Here's our deformation data from the USGS once again. For the last couple days, starting off here, we're coming out of a longer deflation trend. Let's point that out. Here we had this was kind of the bottom. This was the bottom of the deflation curve, which we'll show you shortly, and then we've been coming back out of it, reinflating right up here. And if we look at the past week, we can see the contacts. That was just the last 2 days there and there. And so that was part of a larger deflation inflation event, which are becoming so common now. They happen at least one every few days, and sometimes more than that. Sometimes it happen back to back. We'll have to see if we have another one that comes in short order, and it's once again we'll look at the patterns and try to make some extrapolations, but it doesn't really connect to anything that we can tell on the surface as far as eruption. Interesting to note, and maybe we would see some patterns and learn something new, but there's nothing really that we can link that to easily as of now. So that's the past week. For the past month, we're still blown out by the PEOO station, which is now flatlined. And once this grows off our graph, we'll have our resolution back here. That's kind of what's happened here with this past week graph. Looking at the GPS, the long-term pattern of spread across the caldera continues, right, with some small changes probably related to the deflation inflation events, and so you have these smaller variations on top of this longer term trend of kind of recovery, right? The caldera spreading, which normally is associated with magma coming into the volcano as well. So it's doing that, and this was the first decrease as eruption began, so we relieved a lot of that pressure, and then once the vents changed from the north vent to the west vent, we've seen that change in a direction as well. So that's one thing we're looking at as a possible, leading into a continuation of this eruption, some sort of rejuvenation of it, or the end of this eruption, and this works towards the next eruption. This is all difficult and to predict. It's really something you monitor and then you react to and then try to understand in those kind of terms. So here's the summit, and on the rift zone, we are once again seeing what looks like a possible background level of this extension after a recovery of inflation or spreading across the rift, building up to the eruption, and then a decrease. Ever since then, it seems to have essentially stabilized finally. This had been dropping for a long, long time until just recently it seems like it's changed track a little bit, possibly rising a little bit, seemed like it might be steeper at first, but now with a little bit more data on this right side, if I zoom way in here, with a little more data, you can see it looks more like the background amount. So once again, GPS is slow to come in. You have to wait and see over the weeks and months. So, but there it is. Looking at the depth of the lava lake, we essentially have slowed our rate. We've only come up 1 meter or 3 feet since the last week, and so it may still slowly be rising. It could be that deflation inflations are slowing that process as well, as has happened in previous weeks. And so that might be the biggest effect there of that deflation inflation cycle is changing the nozzle and how the lava comes out. So hard to really see here, but if I zoom way in, we're looking at a plateau in that zone right in here. Okay, so our current number is 222 meters, 728 feet. This is from the USGS directly. And most recent SO2 measurement, March 18th, was 700 tons per day. The day before that, it was 650 tons per day. So these are low values still. We'll show you the plot here shortly. I'm just kind of scanning through the rest of the HVO daily update. It talks about intermittent foundering of a thin crust continuing in the active western portion of the lava lake. And still continuing, the eastern portion of the lava lake is approximately 5 meters, 16 feet lower than the active western portion. Those are the highlights there, and there's more information if you want to go read more details for yourself. And here is the SO2 plot. So our most recent measurements, 700 and 650 are there and there. And our scale from 1200 to 300, so not quite 1,000 top to bottom. And some small variations that we speculated in the past and may have something to do with this variability of deflation inflation on a volcano as well. So all still within a fairly low range, and it's seemingly, if anything, the average may be slowly going down. We'll have to wait and see. The SO2 is so important, of course, because it's been linked to the effusion rate, the amount of lava coming out of the volcano in the past. So that's something we definitely keep an eye on as a proxy for how much lava might be coming out, or if there's lava coming out, the gassiness, the gas content of it may be related to that as well. So long term, we started off at 50,000 tons per day in the first few days and have really plateaued off and are down really below 1,000 now. And so really dropped off substantially since the eruption began. Nevertheless, there's still VOG, and it's smellier closer to the source before the gas reacts with the water vapor in the air and forms more of the particulates. And so you can have particulates elsewhere. Of course, if it's pouring rain, then you won't see it as much. But the weather's been a little crazy, and there could be particulates or gas smell possibly anywhere around here, as far as we can tell, based on this VOG mapping project from Manoa. All right, so one last thing here. USGS has also released a video of the lower East Rift Zone. So this is a routine helicopter overflight of the East Rift Zone that allowed HVO geologists to conduct an updated visual and thermal survey. It's shown at 5 times speed and follows a coastline from Kapoho to Pohoiki and then past the Mackenzie area. And they note lava along the shoreline continues to slowly erode with small beaches forming in embayments. So I'll play this for you guys, and then we'll take a break and field some questions. And yeah, we'll go from there. So check out here the view. 5 times speed, small island here at the bottom. I'm going to view moving from Poho to the southwest now. Lots of coastal erosion happening. You see some small areas of beach. Actually, quite a lot of areas of beach piling up, and quite a lot of lava peninsulas sticking out into the surf as well. So there it is. That's the eastern portion of the flow. Here comes Pohoiki Beach into view. The new black sand beach blocking the fishing harbor. And here's the Mackenzie flow, the 3 entries that lasted 3 days in the initial part of the eruption. Right, so that's the USGS video, and then we'll take a break here, and we will turn to some questions, Dane.
All right.
Well, before we do that, do want to thank hawaiitracker.com helping make this possible. Best way you can help support us if you like this type of content is to like, subscribe, and share this video. We don't have advertising revenue to be able to help pay for that kind of stuff, so we rely on word of mouth to be able to get the information out there, help spread the word. We also are building up our own social media platform on hawaiitracker.com. Consider becoming a member there. We are also taking monetary donations on hawaiitracker.com/support. If you feel like helping us out that way, it goes a long ways. So with that, let's go into some questions. Actually, before we do that, we do have some donations I want to mention. So, sorry. Donations that I wanted to mention. The Dave P, Charlie Smith, and Maxine C. really appreciate it. Helping with that, cash flow. And with that, let's get into some of these questions. We do not have that many actually today. I'm seeing some more getting tossed in chat right now, but let's go through the one that we do have here. KL asks about the lava lake. When the crust gets thicker and thicker, could this lake eventually become a new shallow magma chamber? And if so, how would that, or what would that process look like to make a magma chamber to you?
Yeah, I mean, it's really interesting. That's an interesting thing to think about, because at some point it comes down to a technicality of how you think of it, right? So when you take Geology 101, you learn that magma is still underground and lava is when it's been exposed to the surface, right? So if you follow me here, if you actually had the lava lake crust all the way over, let's say, but still be fed from below and still be lifting that crust, where mostly it was just filling now underground, because technically it's crusted over and it's underground, technically, right? Then possibly it could be being placed as a magma body at that point in time. Maybe you could switch from being lava flow to having it be a magma flow. I don't know. Maybe that's something more exotic that has never really crossed my mind before as a technicality, but maybe, and that would require eruption to crust all the way over on the surface, but keep going from below, despite being drowned and covered over. Yeah.
Yeah, and just keep churning in there below the crusted surface.
Yeah, and that could happen, and it could be that occasionally from time to time it does burst out of the crust onto the surface of that crust and make smaller lava flows on top of that, beyond the whole filling from below process, right? So, I mean, it's totally possible. At some point, it becomes a caldera crater floor, and crater floors can't uplift from magma injecting below it. So, yeah, at some point, it is a matter of definition of what point is it magma or lava or part of the magma chamber or cooled lava flow with a very thick crust, right? So yeah, interesting to think about, and it doesn't necessarily I suppose matter as the curiosity of it is enough to kind of entertain us. So mahalo for that question, KL.
All right, we do have 2 super chats that just came through. Jeffrey Christian and Natasha. Jeffrey with a $19.99 super chat. Natasha with a $5 super chat. No messages in either of those. Appreciate it, guys. Really helps out. So kind of goes into the previous question, does kind of play into the next question a little bit in some ways. Is it true that the lava flows back into the volcano?
A lot of times, yes. I mean, it's what the lava, what an eruption is really about is, if you one real way one way to put an analogy into it, it's not totally accurate, right? But it's kind of like burping a baby. It's just about getting the gas out of the volcano, and once the gas is out, the volcano is happy, and the lava then can go to the lowest possible place, which can be a crack, which can be the same crack that it came out of, and flow back in where it was going. It's all about burping out, releasing the gas. Right? So if there's a way to release the gas without the lava actually pouring out of the surface, it would just do that. That is essentially what the 2008 to 18 era was about. We had a lava lake up there. It would rose and net all the way up and spilled over. But throughout that time, it was just bubbling out, bubbling out, bubbling out, bubbling out every second, every minute of every day. That was its main purpose, was that gas vent out of the volcano. That's what it really accomplished. And it was also because it was such a good vent, it was reflecting the rise in the magma pressure in the chamber, which came all the way up to the surface. Right, so really interesting to think about that. So yeah, lava does flow back in the volcano. You see it locally around fissures a lot of times. You still see the remains of the fissures, but it's hard to see the bottom of a fissure many times because lava, when you look at it, you don't see the actual bare crack of the ground when it originally cracked open. You see that lava has coated that crack, and normally it's flowing back in at least a little bit before the eruption ends, back into the crack, which is the lowest point in the area. So that's kind of in the surface sense. We have reviewed the USGS papers about deflation inflation events, suggesting that the mechanism for having deflation inflation is some movement in the magma chamber itself of denser magma going down and less dense, gassier, hotter magma coming up and kind of moving past each other through some kind of like a skinny hallway kind of thing. You can't both go side by side. One comes through, then when that batch is through, the other one can take its turn and go the other way, right? So certainly we can see the magma moving within the shallow parts of the magma chamber, and we also had the whole example of the north vent in this eruption that lava was draining back into it, and that changed, it seems, the whole dynamics underground to the point where we saw the change in the GPS and the tilt and everything has been reflected ever since then, which is one of the more fascinating things I'm waiting to hear about more as we research this, as USGS and colleagues research this in the years to come.
All right. We do have a $25 super chat just came through from Brenda Palmentier. Thanks for all you do for us volcano nerds. Appreciate it. So kind of my question, or the question I'm seeing a little bit, I'm going to rephrase. Is it possible so we're having this crusted over phase of the lava lake continually growing over the past couple months. Is it possible for that crust to then become liquid or a molten form again if, say, activity increases or a resurfacing were to happen?
I think it would be difficult personally for it to remelt. It all depends how thick it is, and it depends how soon something tried to remelt it. I mean, so the best way for that to happen would be for there to be a new vent higher up on a crater wall that poured a whole bunch of lava over top of it. So if it has hot lava above it and below it, then that has a better chance of possibly melting all the way. But there might be some chunk of it still where it doesn't melt all the way. That's, we see it even in plate tectonics, those big slabs of crust sink all the way to the bottom of the flowing liquid mantle, or liquid on a time scale of the mantle flow anyways. Right. So, yeah.
Christina Anderson from Kona asks about how much longer do you think the eruption could last? Are we talking months or longer potentially, or shorter?
Yeah, great question. I've been wrong everything so far, so I'm not sure it's worth asking me. But
the science is chugging along, with like no pressure, it feels like, but still going.
Yeah, we'll see. If the gas values are just very slowly going down, just like the lava lakes just goes up 1 meter a week, the gas values go down 100 tons per day a week. And at that rate, it might still be 2 months before it gets to zero, which is still a while, right? But it seems like it isn't on a downward trend. So I don't think it lasts indefinitely, but it could be a few more months, right? Now, the thing is, whatever signal is causing the extension and the uplift of the crater rim, if that magma comes and finds its way out of this vent, then it could reinvigorate it, and then it could just we'll have to reset and reassess from scratch, right? So that's the big X factor there. Is it seems the long-term supply is still there, and that signal of the caldera is the one that would indicate, even if this one does end soon, that there will be another one that might come not long afterwards.
What is the question is what's the current depth of the lava lake, and has it changed recently?
The current depth is
talk with this, but
it is 728 feet or 222 meters, and it has only changed 1 meter or 3 feet since last week. And so that's just a net change. It may be fluctuating up and down, as we showed you guys in the tilt plot. The pressure has been up and down, and so that would not be surprising. So a net gain of only 1 meter, 3 feet.
Well, that does it for this round of questions. We will be doing one more round at the end. You want to take it away?
Yeah. So I'm just gonna introduce here. There's a feature on HawaiiTracker.com. I'm going to show you guys a couple of our photographers that are featured on here. So, for example, here's a submission by Warren Fintz, Halemaʻumaʻu Moonbow, and you can see that on a tracker website. If you actually like any of these images, you could directly click on the buy print and support these photographers directly. So one way to support the people who are contributing to Hawaii Tracker, besides guys like us making videos, you can go on there and find, look at these photographs, and you can check them out here. Really nice one. I should do it better justice if I would zoom in a little more for you guys here. So there we go, Warren Fintz. And that's one, just one that's come up recently. And here's another one that is a weekly poster, and Corey B. Aloha Friday, Kona Sunset. This one's from last week, but you can come find more similar ones on there as well. Likewise, you can check out those views here. Since we are Aloha Friday, I thought I'd show that off here before we switch gears and go into the Maunaloa part of the update. All right, so Maunaloa. We'll start off by looking at our earthquakes map.
Before we jump in there, we have a $10 super chat from Les Hefner. You guys rock as usual with the geology pun in there. Appreciate it.
Mahalo, Les, mahalo. All right, so getting into a Maunaloa update here on Friday, March 19th, 2021. We can see that the most recent activity in earthquakes on the island is this cluster on this northeast flank of Maunaloa. There are a couple earthquakes around Kīlauea summit and a couple by its south flank, but that's essentially been background lower activity, common in the past few weeks and months since eruption began in late 2020. Our Dipahala cluster is still active and is unrelated to surface activity, apart from the fact that it seems to validate the notion of increased supply to both volcanoes of Maunaloa and Kīlauea. When we zoom in here in Maunaloa, there's been this summit earthquake pattern, which is ongoing, but still fairly slow. And the more recent cluster is this one here in the northeast flank. So if I zoom in on here, you can see a little bit better where these are. They're south of this northeast rift of Maunaloa. And of these, the largest earthquake, if I scroll down here on the left, and I know you guys probably can't read or see any of these numbers. Let's see if the numbers at least on the screen there. And maybe what I'll do is we'll sort by largest magnitude first. And let's zoom in once again here. And so our 3.5 was the largest down here, 2.4 kilometers above sea level. Next, the 3.1, there it is, 1.6 kilometers above sea level. Next, the 2.8, 1.5 above sea level. 2.6, 1.8 above, 2.5, and kind of go on. 2.5 and below, there's quite a few. Those were the biggest ones that I just mentioned there. So there's been an info statement put out by the USGS, and here it is. They put this out yesterday evening. At that point in time, they described over 40 earthquakes beneath the upper Kaʻōiki seismic zone. The cluster was 1 mile wide and half a mile to 4 miles below the surface. And they will note here, and I will read this: clustering of shallow earthquakes in this region does not mean an eruption is imminent. HVO has recorded shallow earthquakes in this area for many decades across several eruptive cycles at both Kīlauea and Maunaloa. These earthquakes do not show any sign of magmatic involvement and are part of normal readjustments of the volcano due to the changing stresses within it. Other monitoring data streams for Kīlauea and Maunaloa, including ground deformation, gas, and imagery, show no signs of increased activity. And onwards from there. So that's the relevant part there. let's show you guys a little bit more about that. So we'll refer back to this paper by Walter and Amalung, Stress Transfer at Maunaloa, which delimits several of these earthquake zones. There's a Kaʻōiki, the Kīlauea, and a Kona area. And the reason being that these are different areas of the volcano that relate to different flanks of the volcano, changes within it in slightly different ways, depending on which rift zone might be more active or which part of the summit, et cetera, et cetera. So Kawiki is one that's interesting because it preceded, most recently there was a magnitude 6.6 which occurred there, preceding the 1984 eruption by several months. And there have been other cases where there have been big earthquakes in this area that have also ultimately led, many months later, they've kind of announced the reawakening next stage of Mauna Loa. So we have not had that yet. We have not had any reawakening size earthquake anywhere yet, and that's something that we would await and anticipate would happen at some point in time. We don't know exactly when. That would portend some change in the eruption there. So in any case, we can take this area and we can superimpose our earthquakes on it. I just have a screenshot here of this, and I'll zoom in there. These fall within that polygon area right in there of that Kaʻōiki upper zone. And so this is just a map view of it. It's kind of difficult to see. So we'll show you the same cross section I showed you guys a couple weeks ago when we had other earthquakes in Kaʻōiki as well. And here we have a cross section from that same paper. So we have the magma system Maunaloa over here. Magma system Kīlauea is over here, and in the hard rocks in between them, the Kaʻōiki zone, right? And there's an area that's close to the surface up here where the earthquakes are happening now. That's a more strike-slip kind of movement, right lateral slip of the ground surface without much vertical movement. And at the same time, there seems to also be movement along the base of this volcanic pile. And so there could be some curved connection, as is often the case, as we see underneath, for example, the south flank of Kīlauea. Right? So, in fact, the USGS Volcano Watch describes how this area may well be some drowned area of the south flank of Mauna Loa that Kīlauea has then grown through and on top of. And essentially, for that reason, it may have stopped moving as much, but it still exists as a weakness, as a fault structure buried in the volcano. So as both this magma chamber and this magma chamber have changes, this is an area that slides back and forth. So what this tells you is that there's a relative change between Kīlauea and Mauna Loa. There have been times where this has actually been connected to Kīlauea's eruptions and intrusions of its rift zones and summit. So in either case, there are times where this happens before events and sometimes it happens afterwards. So we'll have to really wait and see which of those we're looking at. As far as earthquake rates for the whole year here, we're looking at earthquakes per week here, and we're maxing out at 250 as our value, which occurred about a month ago. Since then, we're down around 150 earthquakes per week, right? And per week is not enough to cause us concern as if we're building towards an eruption imminently. Long term, yes. Short term, no. Past month, here we are peaking over 40 earthquakes per day. That's higher than we've seen in a little while, but it's not high enough to cause concern as well. And so to really put things in perspective, I'm going to bring this back up. These are plots put up by Frank Truesdell during his recent Mauna Loa volcano talk. And what you can see here is if I zoom in, number of earthquakes per day, the top of this graph is 1,500. 1,500. And eruption happens in this red line over here. Right? So we're looking at essentially, this is day 460, let's call it. So we're looking at over a year before the eruption. Right? You're seeing the background level isn't just spiking to those 50 per days. It's actually background 50 per day, and it's spiking to 1,000 per day. And it's background climbing to 500 per day. Over here we had, it looks like maybe a whole month of it being close to 400 earthquakes per day. Then an eruption at the summit. Okay, that's 1975. Here's 1984. Once again, Frank Truesdell from the HVO talk. And slightly different plot here. I believe this is per hour, but you can see the earthquake frequency. Here is eruption. right in here, you actually had a buildup of earthquakes per hour to where it was peaking. In this case, it was somewhere around 20 earthquakes per hour. And other times you were having background levels of 5 or 10 earthquakes per hour for several weeks ahead of that eruption as well. Right? And certainly right before the eruption began, there was a big spike that was up to over 100 per hour.
We have a 1999 super chat from 12 time 12. Says thanks for the info. I appreciate it.
Mahalo, mahalo. And that's how we compare to 1984. And you can see that if we look at the last 2 years, this is the plot presented back in January, so it doesn't have quite the most recent stuff. But even still, you can see that the spikes of earthquakes per day now compared on the bottom and not the per week. If we look at per week, then yeah, you can get to this 400 or 500 value. You might think, okay, maybe we're getting there. But it's important to note the difference between per week and per day. So per day, spiking to, there's a 200, there's a 150, there's almost a 150. The spikes are getting to 150, and the background level is somewhere back here below 50 per day. Right? So that's where we are. That's the pattern we're seeing, and the pattern we need to see is this other one where we're spiking to 1,000, 1,500 per day, and the background level is in the hundreds. That's the difference in scale that we're looking for. Building up to an eruption sooner where really it's time to be packing go bags and all that. In the meantime, just make sure you know what a go bag is, and start making emergency planning and that kind of thing, just as a preparation, not because anything has changed in the volcano. Looking at tilt and GPS, we just see very small tilt cycles, half microradian up, half microradian down. Just the daily cycles there, nothing really volcanic to look at. Looking at the past month, we're still blown out by that big spike of the tilt meter shaking during an earthquake, and all the changes have all been small besides that, which is good enough. Essentially, we're flatlined. As far as a GPS cross-caldera distance change, you can see that we're still waiting to see what trend. We still seem to be coming on an upward trend. Let's zoom in on that. All right, let me zoom over to the left so you guys can see we're looking at meters of distance across the summit caldera of Maunaloa. And so 0.01 is 1 centimeter, 2 centimeters, 3 centimeters. Right, that's the scale we're looking at there. So the long-term trend has been upwards for a while, more on that here shortly, but let's look at the most recent pattern, which is that since January, it's been a more steep upward trend right up here. And it's not clear over here if we're continuing at that rate or if there's some change maybe going on, and that's just all a big question mark that hasn't come on the graph to really see yet. The reason being, just like the Pu'o'o data, you might have some background level and then something local happening just through there, right? And I'll lead to this here shortly. But first, the long-term trend is this. You can see this is the past 5 years. A little more slowly, a little more quickly, a little more slowly, a little more quickly. Rates of inflation, of spreading of the caldera line, right? And because you can have that kind of local effect, let's look in more detail at that since it's come up before. I want to point out that this is a previous 5-year plot from a couple years ago. Here is captured in a zone of 2015 when we had another steep rise in the GPS caldera distance, and a slowing down, a flattening, and then it kept rising again. It's still rising essentially since then. We can have these accelerations and stabilizations and variations in a shorter term that do not necessarily lead to eruption on their own. I think this is worth pointing out. And as well, the fact that during Frank Truesdale's talk, put in this plot of the last 6 months GPS, July 2020 to January 2020. I'm going to zoom way in here, right? Because the distance that we're looking at is between this station and this station in Maunaloa. So this distance across the caldera right over here. And if you'll notice, the station on the north side of the caldera is moving to the south. And typically, the one on the south is the one moving to the south, and the one on the north is moving to the north, and that's how they get farther apart. Well, during this period of time, which is that same period of the contraction of the GPS signal, we actually see it moving to the south. If I advance to look at just December to January of 2021, I'm going to zoom way in once again, you can see that by now it's changed directions. Now it's pointing more that way, right? So normally one way it's hard to really see how these might all fall in sequence, but a dividing line between a direction of all these arrows is something like that, perhaps. It's not clear, maybe through here or maybe through here. Right? That's kind of the locus of where everything is moving away in every direction from there. In the more recent month, and if you go further back in time, I'm going to scroll up here too, then there's something that's happening. The center is more over here, more to the northwest. So that's how volcanoes grow, is by, you know, putting different magma bodies in different parts of the volcano. That could have happened. There could have been some other event that happened over here that caused this temporary shift in the direction of the GPS. In any case, that's a kind of local effect that could be affecting the signal that you see here. And that's why we're still waiting to see what might come of the right end of the signal as the progression continues. So just this on its own is not enough to cause alarm. The earthquakes themselves are not enough to cause alarm. Earthquake rates are still insufficient. And accordingly, the USGS update on Maunaloa issued this past Thursday. It says that data streams on Maunaloa remain stable and show no signs of increased activity, apart from the shallow swarm of shallow seismicity that began under the upper Kaʻōiki seismic zone. That is essentially it. And there is some other information here, but essentially, as I read before, clustering of shallow earthquakes in this region does not mean an eruption is imminent. Right, so that is a text update. And a little more about why might earthquakes occur. We're going to do a little bit more detail on some earthquakes today before our final round of questions. And this is an older volcano watch back to 2012, and no images from that point in time. But I wanted to read a little bit more about Kawiki for you guys from the USGS, right? And they talk about how that 6.6 in 1983 actually set off an aftershock sequence that has been active essentially ever since then. So since the 1980s, there have been earthquakes in that upper Kaʻōiki area, and I will read this part here. So after November 1983, the average of earthquakes in upper Kaʻōiki at least tripled and included 5 notable seismic swarms. Swarms in 1990-93 did precede intrusions in Kīlauea's upper east rift zone by a few months. Swarms in 1997 2006 did not immediately precede any change in activity. Several of these swarms, but not all, included a magnitude 4.0 or greater earthquake. All right, then they actually refer to a swarm that occurred in 2012 and talk about how Kaʻōiki Pali is one of a series of subparallel faults that extends from the area west of Namakani Campground at the summit of the national park all the way to Honuapo. These faults form the Kaʻōiki-Honuapo fault system, were probably created by subsidence on Mauna Loa's southeast flank before Kīlauea was built against or on it. You can see the surface expression of these faults in the stepped terrain just mauka of Highway 11 between Kilauea's summit and Pahala. And I will read on because this is good information. But the fact that the steps are draped by an unbroken 9,000-year-old lava flow shows that if these faults are still active at depths, their movements are too minor to result in a surface rupture, despite the earthquakes centered there. This is reaffirmed in 2012 by the lack of any ground shift or any shift of the ground surface in response to the recent earthquakes. The entire southeast flank of Mauna Loa frequently hosts earthquakes in response to being squeezed and stretched between two very active volcanoes. And earthquakes in 74 and 83 believed to have enabled Mauna Loa's eruptions in 75 and 84. So there's that. There is that downward motion of normal faults. There's the strike-slip manner mentioned in here. I won't read anymore. And you basically essentially see that swarms on Kawiki Pali are probably not directly connected with subsurface magma movement, but may be linked to changes in the pressure within Kīlauea's magma system. So Kīlauea or Mauna Loa, some combination thereof, but that doesn't necessarily point like a conclusive, finger towards Mauna Loa. So that's the 2012 swarm, and I wanted to show you guys this. This is a little bonus treat here. Here's a view of earthquakes. I'm going to show you guys today just a period from 1986 to 1996, compiled from the USGS. They've relocated the earthquakes to try to get a more accurate, and when you do that, you can see some of these seismic structures a little bit more easily here. So I'm going to zoom in here. Something to add in before I start this?
Yep, we have a $35 super chat from one of our regulars, Gary Bryan. He says, appreciate all you guys do behind the scenes as well as your preparation for these updates. Thank you, Gary.
Mahalo,
a lot
Gary.
goes into them.
Mahalo,
Right.
yeah. I was stoked to find this to share with you guys here. This would show you guys just one view of these kind of things. So this is actually a time-lapse animation of earthquakes from 1986 to 1996. And so let me start it here. Start at the beginning, and I'll have to pan over. I've sped it up quite a bit, so it didn't take a whole 10 minutes to go across them, but it's basically adding them to the area as they're occurring. So it's about a year per second here, the way I have it set up. Right? So you can really see the upper Kaʻōiki system right up here, active between 1980s and 1990s, quite a bit already right there. So you see that there's that zone right there. There's almost a connecting zone right in here, like a big arc, and that's what we refer to as that in that cross section I showed you guys, that separation between magma systems of Maunaloa and of Kīlauea. Maunaloa is very quiet during that era. Kīlauea was feeding the Pu'u'o eruption. You see a lot of upper east rift zone activity, as well as if I zoom in here, there's actually a gap right in there, and then the south flank patches, right? There's discrete patches. There's this big patch like that. There's another patch over here, another patch over here, which are especially seismically active, and some other patches further down as well. So let me zoom in on a Kawiki. Let me try to play it back for you guys. I zoomed all the way in on Kawiki, if I can manage that. So there it is. You can kind of see how frequent and how common earthquakes in this Kaʻōiki seismic zone are. And this entire time with Maunaloa is not doing anything, it was all Kīlauea, in fact. So still interesting to note, still interesting to talk about. It is much closer to Maunaloa Summit than to Kīlauea Summit, but it may well be more directly connected to Kīlauea. Possibly to both.
Right. It's a really good representation there, that time-lapse animation. And I think there's since I got it up, 4 earthquakes associated from that region, 4 large earthquakes, magnitude 6 plus, that are associated with Northeast Rift Zone eruption, were 1852, 1880, 1941, and then 1983-84 into that sequence.
Yeah, so 4 times, yeah. And of course there are other sequences in the Kīlauea and the Kona side, right? So that's where it was,
right. And then, then you also have 4 on that side too, 1868, 1887, 1918, 1919, and 1950, the big 1950 eruption.
Yeah, it's interesting. Yeah, so you guys can see it. So we'll see that, the big earthquake that signals a shift in Mauna Loa to the next phase of awakening may not occur in Kaʻōiki. It may occur somewhere else as well. Yeah, and where it occurs will tell us something about the dynamics of the eruption. So I want to take you guys a little bit more in depth on the USGS Mauna Loa monitoring map here, just show you guys how I use this a little bit, so you guys can see if there is some fake news spreading around. You want to go check out what's going on. I show you a little bit of how we can look at this, right? So if you just go to the main USGS homepage and click on Mauna Loa monitoring, then this is the map that comes up right in here. There's a lot of stuff on here. So over here on the right, I click on my instruments visible, and I'm gonna just hide all the instruments. Right? Let's see if I can get my earthquakes visible over here. There's my earthquake list. It's a little bit, I don't have as much screen estate as I would like here, but which is why I don't usually use this page. But it does have some other tools. So let's zoom in here to that cluster right over there. And then what I can do is I can come over here and click on earthquake plots and select plot area. I know this is kind of hard for everyone to see potentially, right? But I'm gonna read it as I go, as I'm doing here. And the default 10-kilometer cross section is fine. So let's put our first point over here and our second point over here, and it's going to draw a box around those earthquakes. And then over here we can click on view plot, and hopefully this works. And so there you can see the sequence of earthquakes with, on a bottom axis, is time. So this is by default a week, or actually here it's close to a month in this case. This is 319 and this is 222, so this is about a month on the bottom. And then depth here, 0.6 miles above sea level and 1.9 above sea level. So you can kind of see that there is a whole vertical shaft of these things, yeah, which may indicate some movement on that vertical surface, whether it's in and out of the screen, kind of that lateral shift with not a whole lot of ground on the surface, or if it's more of the slipping down on one side. It's not quite clear. We're looking more to the individual earthquakes, but we don't have that quite ready here. So, but this is the kind of thing you can look at. If you're imagining magma coming from depth, you would imagine you'd like to see those patterns coming up from a long way down, much deeper than just right here. And we'll show you guys some examples of Kīlauea here shortly of that. So that is we can do it. One of the things you can do in Maunaloa with these plots is look at that cross section, right? So let's hide the plot here, and now I want to put my instruments back on. Show all. And I'm curious, was there any kind of tremor? Perhaps was there magma moving underground with this event? And you have to find one of these stations that actually has data. So let's see, maybe this MLOA station has data, so you can click on it. And let's go back here to the past 48 hours. And you can see something going on in here, but I think it was blank. There might have been some issue with the station, perhaps. Maybe a little bit of increased tremor in here a little bit, but nothing really convincing. There's really not a whole lot on there. You do see a lot of these discrete wiggles that have an earthquake shape. This is a typical earthquake shape. And this does not look quite like an earthquake, maybe wind or rain, or not quite clear what's going on there. Right? This is a bigger earthquake right in here. That might have been that bigger earthquake. Those bigger threes might have been those ones in there. So not a whole lot of tremor, more discrete earthquakes, more like a fault adjustment rather than any direct magmatic movement. Of course, once the volcanoes do adjust, magma can then adjust secondarily as well. But it doesn't seem like there was a giant pulse that came in that caused any of this to happen. So this is where you can get a lot of information straight from this monitoring page right there. So to kind of tie it back into Kīlauea with the earthquakes here, today's volcano watch, yesterday's volcano watch this week by the USGS once again, written by HVO. It relates to using ocean swells and the background noise of seismology as a signal that can detect changes in the variations of seismic signals through the ground. And the reasons those variations might occur is because essentially cracks might open and close as a result of magma pressure coming in or going out. And depending on how open or closed those cracks are, the more noise and scatter you have in the movement of energy through the crust. And if you're measuring the background level of that, then you can make some inferences, right? And this is kind of a more recent, it's been ongoing for a while already, but a more recent trend in research and technique in seismology here. You can see the station taken by N. Bennington of installation of one of these temporary seismometers. And so they actually are talking about how they've installed these and used this technique to better understand what happened in 2018 as well. And in particular, they note, and we'll look into this in a little more detail, there was a magnitude 5.3 earthquakes a year earlier that had significantly weakened the crust directly beneath Pu'o'o. And so that was a warning sign. And of course, when you're developing a technique, maybe you don't have enough confidence to say, well, there's a change there, and therefore something's definitely going to happen by Pu'o'o. But looking in hindsight, it's something that certainly is evident in the data. So in any case, that allowed HVO scientists to hypothesize that the combination of increased pressure at the summit and a weakening the shallow crust beneath Pu'o'o might have been the conditions favorable for magma to move down a rift and erupt in 2018. So recently they deployed 8 additional temporary seismometers around Halemaʻumaʻu at the summit to track magma movements beneath a new lava lake. So that means denser sampling where physical changes are occurring under the crater, and the reason why is because they want to answer questions such as, where is the magma source and where are the pathways for the eruption? Can we understand small increases and decreases in activity through changes in this background characterization as well? Can this technique provide clues for when eruption will end? And how can we use what we've learned to better understand and forecast activity with future eruptions? That's where they're going with this. And so since that's a lot of reading, I want to turn here to the reference, the study done in 2018, and showing you guys this 5.3. This is a paper by Flinders, Caldon, Johansson, Tyra, Shiro, and Haney. And you can see here, they've noted the location of that 5.3 earthquake, which occurred June 8th, 2017. So the previous summer, that was the one that loosened and opened enough cracks to the point where the seismic background was detected to change. And of course, if that's how much cracking you have on the ground, then maybe that allows the magma to also inject, and that's how it's related. So you can kind of see with the triangles and the circles here, that's the locations of the instruments and different stages of deployment as well. So maybe I can zoom that in a little more for you guys to see better. So there it is there. And most important here is that earthquake at 5.3. Of course, there was that later 6.9 occurred over here nearby. So that was a couple days after the eruption began, and that was also part of the sequence, allowing a larger movement of magma from the summit through the rift zone, right? That part of that cascading sequence of events. Okay, so the 5.3 is noted there. And as well, there were 3 deep lower crustal swarms of earthquakes. And so let's zoom into this as well. And what you can see is our depth on the left here in kilometers, 0, 4, 8, 12. So from below 12 kilometers, we're talking a range of, 10 miles-ish. You're having these vertical swarms of earthquakes occurring. There's 1 in purple, there's 2, there's 3. The first one occurring somewhere around March 6, 2018, right? That's ahead. So these 3 ones kind of were the first warning signs, these vertical shafts right in there. And then you have a lot of shallow stuff happening in this teal zone before you have the eruption occurring over here at the end of the orange zone. All right, so that's what you might look like. If we saw this in Maunaloa from these kind of depths coming all the way up from the lower crust, then you might say, okay, well, something's going to happen. In Kīlauea, it still took from March until May for it to manifest fully after 3 bursts of that activity, right? So we haven't seen anything like this yet, and that would be another clue for Maunaloa, something to look for. Maybe we'll see it, maybe we won't. We'll just put that in our tool belt and hope for the best. See what you can see. So here is a plot. And let's zoom in on this green one here of the East Rift Zone. And so let me show you guys what this actually, it's not the most easy to understand, but essentially what you're looking for is the variation of velocity as a percentage of the total velocity. So it's like, how much is the variation? Just think of it as a measure of that, and that's good enough. And so you can see that there are other changes that occur. Let's see if I can, there are some changes that occur, some variations up and down. They're not directly related, right? So you can kind of see the baseline essentially is the same with some shorter term variations. But what they're noting is that after this 5.3, which occurs here in 2017, the baseline actually drops down and stays down for a while, indicating a change in the ambient stress conditions around the East Rift Zone. And so in hindsight, that's not surprising. And of course, this right side of it here is when eruption begins, and then things really change a lot because magma is flowing and cracks are opening all over the place at a much higher rate. So that's the East Rift Zone. The summit has some different signals, and Southwest Rift Zone as well. Without going into detail of those, I will skip down here and show you guys what's the Southwest Rift Zone. Whoa, and here we go, this one being the summit. So we're looking at this era of blue in here as a time when there was an increase, right? Possibly because the cracks had closed, because a magma chamber had swelled so much, all the cracks had closed, was squeezing them all closed, and that allowed there to be an increase in that signal before the eruption as well. So all that ahead of that 6.9 earthquake, which occurs. So interesting to see these kind of changes, something that hopefully is monitored in real time and publicly available in the future as well. So fascinating, but that's why they're deploying these instruments over the lava lake, so look for these kind of changes happening that may relate to opening and closing of cracks, and therefore magma movements and pressure in the ground and that kind of thing.
Can you show that paper for me? People are asking which one it is.
I will scroll back up to the top. This is directly linked in the Volcano Watch, right? So let me show you guys here. This is a Volcano Watch on the USGS page. And if you scroll down over here, it says HVO scientists recently applied this technique, and that recently applied this technique is a link. You click on that, and we'll go through it for you guys. Click on that. It takes you to the pubs USGS page. You can click on the DOI link there. And that leads you to open access online paper right here. And what I was just showing you guys was the PDF that you get to just like that. So that's where it is. There's a lot of information in there, so you guys can go and look at more on that. I'm not going to do it justice beyond what I initially just showed right there. There is one more figure to show you guys here. Pre-eruptive increase at the summit, shown by a different technique here as well. So interesting stuff. Kind of a different technique. It's something that people aren't used to looking at that necessarily. It's usually, was there an earthquake? How big was it, and where was it? And that's all as far as people would normally get. So there's a lot more to it than this. So that's why we leave it to the USGS to really present this information to us. And with that, we conclude the update portion. We can turn to some questions here, and we'll wrap up and sign off, Dane.
All right. Well, let's get into some questions. We did have a one more donation I wanted to shout out on hawaiitracker.com from Craig L. Really appreciate it.
Hello, Craig.
All right, so we do have a bunch of different questions here. Let's try and focus them a little bit. So you're just talking about the faults, so let's focus on those to start out with. First one is about the standby. All right, so when you're talking about faults on the Maunaloa, the ones that we were looking at today, what types of faults are they? Thrust or strike slip or combination? It's a question from Nicholas on YouTube.
Combination. Let me pull up the graphic here again, which is weird. I have a lot of graphics, as you guys just saw them all. So, you guys right in here. So let's see if zoom in on there, right? Okay. So this upper portion of Kaʻōiki is strike slip, the shallower portion, and then this lower portion is essentially a normal fault, but it gets complicated because the shape of Maunaloa has actually deformed its basal detachment and bowed it down. So there are portions where it has to actually go uphill over a hump before it can resume what's a traditional normal fault basal motion like that, right? So if that makes sense. So it could actually possibly go uphill, but the net motion, long term, should be downhill. But locally under Kawiki, it may well be kind of like a low angle thrust a little bit. It's tricky. That's why it's tricky, right? But overall, it's essentially a normal fault movement, basal movement of Maunaloa, very consistent with that. The angle might be a little unusual. At the surface, there seems to be more of a strike slip component. And that's why when we show, where was it? When we show these kind of beach ball diagrams in here, you see here, right? This is the one showing a strike slip component. This is the one showing that normal motion component. And that's sliding, separating, and moving sideways, more sideways.
Mm-hmm. Well, that really does answer the next question, which was about those beach balls and the focal mechanisms. Just kind of what do they mean?
We'll do that in detail some other time. Yeah, that's right. Like a geology lesson of its own. But it's what it's meant to show is which quadrants of hemispherical projection are having directions of movement, right? So whether movements being compression or extension on different quadrants, and kind of the boundary lines between them in this case, when you see something like this and this, that indicates a vertical fault, either in this orientation or in this orientation. In this case, it's this orientation, the geology of the area. And then over here, it's a similar kind of thing, except instead of up and down, if you cut the beach ball in half horizontally, you'd have a circle, right? So the closer your arc is to a circle, the shallower your fault. So then you have that shallow component there, and then this one here being a little bit more of a steeper component to it as well. So you could have some steeper parts, and you can have some shallower parts, and sometimes it may not be clear from one particular event. So anyways, that would be as deep as I get. I'm sure I got something wrong in a brief recap there, but that's the general gist of it. Beach balls.
All right. Question from YouTube is, with modern equipment, would there likely be even more daily earthquakes as the sensitivity of instruments has increased since 1984?
Absolutely. That's something that we've heard Frank Truesdell discuss in that presentation as well. How a lot of those earthquake counts from the previous two plots we've shown didn't include the sensitivity of the earthquakes now. So it's really ideally you'd compare only the ones above 1.6 today to the ones above 1.6 back then, because otherwise you're not really comparing apples to apples. And so that reduces it by a factor of 5 is what he was saying. The earthquakes, the bulk raw earthquakes.
Wow, yeah. Really makes a difference.
Yeah.
We have one question here that I like it. At first glance, you're going to be like, oh yeah, no. But Julie asks on Facebook, is the amount of magma finite? If the state is due to temperature, friction, pressure, how do crustal remnants remain solid?
Let's see if I can.
So I think it's kind of about like the process of eruption, remelt, and is it going to just erupt all the lava and go solid one day and the core stops, or
so
is it able to perpetuate that?
Right, I'm trying to figure out how largely we're going to frame this, right? Because we have done some talks in the hotspot. The hotspot is the large scale magma generation source for our Hawaiian Island volcanoes, and it is an old one, but it seems to be alive and well and still generating magma today. So within a geologic time scale, the magma amount is finite because the hotspots don't last indefinitely. There's a lot of dead hotspots on the planet already, but that's geologic time. It'll probably be way longer than human time. So for a human perspective, it essentially is an infinite supply of magma, right? And maybe what is finite is how much you can bring up at a time, right? The rate at which it can come up, the rate of volume per time. And so that's why we talk about that so much as an important thing, that we really only have approximations of researchers rather than direct measure of that. Yeah, so that's kind of the first part of it, yeah. And then the surface dynamics are, I think, kind of, it's almost like just the surface texture of how the thing is emplacing in the end, right? It's more about how do you get the gas out, and once the gas is out, how does that make my body cool, whether it's in a cooling lava lake or underground or all of that. That may actually become a giant solid plug at some point, right? And then I'm not sure if that's where she's going there.
It's interesting. It's a very conceptual question, and how you think about it personally and how you answer it, type of thing.
But maybe she goes back and looks at that hotspot and the tomography, the imaging of the mantle, right, and imaging of those old crustal slabs that have gone through. And the idea is essentially that there are some, because of the increasing pressure at depth, you could have changes to the mineral structure of those minerals in there, and essentially where they could take up less space, so you can actually have mineral compactions. And by changing the crystallography of the mineral, you then change its properties, including its melting points. and things like that as well. So that could be something to do with it. Maybe that's another string that you could pull at in your research beyond what we've presented already that I haven't really talked about as much.
All right. So this basically sums up most of the questions for today. One of the last ones I'm gonna throw your way is from Christina, and it's about the 2018 eruption pattern, and is the pre-eruption pattern that we're seeing, or that we saw in 2018 anyway, similar to what we're seeing now on Mauna Loa?
Not yet, no, not really. You know, before 2018, we saw several months of high-level background earthquakes in both of Kīlauea's upper east rift zones, or upper rift zones, upper east rift and the southwest rift zone. So it's different. It's different. We're seeing adjustments that are certainly showing that if you hadn't got the message yet, this volcano is alive and it is filling with magma, and it is a question of when it's going to erupt, right? It also is a question of where it's going to erupt. Remember that once the volcano actually erupts, it's likely to go through a summit sequence first before any possible rift activity, and even then, it's like a giant roulette wheel, and it can only go in one little high piece of that entire volcano, and it can't get everybody all at the same time. Right, so that's kind of the sequence we're going to get through and talk about in more detail as time goes on and we approach that next phase of Maunaloa's eruption. But no, we're not there yet.
Right. This one last one I just want to address.
Jonathan asked on YouTube about the Hawaiian hotspots. We do have 2 videos on the Hawaiian hotspots, both over 10 minutes. Just Philip kind of going in through the science step by step. I will be putting out the part 3 of that, just to continue the train on that. I'd recommend checking it out for anybody that has those kind of questions about the hotspots. That does it for me on this end. I appreciate everybody that showed up in the comments, and we'll be back next time.
Yeah, mahalo Dane, mahalo everybody who's supporting our work, even if it's just by sharing, liking, subscribing to our channels, and however you're finding us, whether it's on Facebook or on YouTube or some other way here on Twitter. So mahalo everybody. We're back to you guys on Tuesday. We'll have passed the 3-month milestone at that point in time, and we'll see what changes we continue to see here in slow motion. And until then, for Dane DuPont, I'm Philip Ong, signing off. Aloha.